Hi everyone. In this lecture, I'll just continue with the discussion of LC circuits with diodes in it. So let me just quickly summarize what I discussed in the last class. So we took a series L or a L and C circuit and connected two diodes, back-to-back connected diodes in series with both inductor and capacitor. And then we analyzed what happened when we started with an initial condition or initial voltage across the capacitor with a value Vx, where Vx is much greater than V gamma. So here V gamma is the cut-in voltage of the diode, and I'm just going to use the word called lossy diode model. So what is a lossy diode model is that this model of a diode, where I'm going to assume that the diode in forward bias region can be modeled as a voltage source of value V gamma. This is the IV characteristics of the diode in the forward bias region. And this model, even though it doesn't contain any resistor in it, it actually captures the losses. Okay, the product of the current and voltage, let ID be the current through the diode times V gamma, is always greater than zero. Okay, so therefore diode is always absorbing power, and hence it captures the losses. It captures the lossy nature of the diode. So we then discussed the voltage across the inductor, which was, I'm just assuming we are starting with the initial voltage of Vx across the capacitor. So then the voltage across the inductor is going to start from Vx minus V gamma. We said that it starts from Vx minus V gamma. In one half cycle, it will reach a negative value of minus of Vx minus V gamma. When the current reverses its direction, there was a sudden jump in the inductor voltage, and that value was given by 2V gamma. So this sudden jump in the inductor voltage occurs because of the polarity of, the reversal in the direction of current, because this diode was initially conducting the current. In the next half cycle, this diode will start conducting. So there was a 2V gamma change in the voltage across the diode. So at the end of one full cycle, the voltage across the diode was Vx minus 3V gamma. So if you go through n cycles, it will actually be Vx minus 2n minus 1 V gamma. Okay, the voltage across the diode will keep reducing. So which means the peak current that it will reach every cycle will also keep reducing. Okay, so the overall energy stored in the circuit itself is reducing. And that is reducing because the energy is actually getting lost across the diode. Okay, as current flow, the moment the diode is going to carry any current, it's going to dissipate some power, which means it's going to dissipate some energy. So therefore, the energy in the tank, the overall energy in the tank keeps reducing as a function of time. Now here, shown here is the voltage across the capacitor. Again, it starts from a peak value of Vx. The minimum negative value it comes to is minus of Vx minus 2V gamma. If had there been no diodes in the circuit, then it would have come to a minimum value of minus Vx. But here it's coming to Vx minus 2V gamma. That's because of the losses in the diode. And at every one full cycle, at the end of one full cycle, we said that the peak value actually comes to Vx minus 4V gamma. The voltage reduces by 4V gamma. After the nth cycle, you can generalize it and say it reduces to Vx minus 2nV gamma. Okay. Now, if your Vx minus 2nV gamma, the magnitude of this is less than V gamma, then we said that the voltage would remain as it is. It will just stay. After that, there won't be any transfer of energy back and forth. Because in this condition, if you remember the previous lecture, we discussed the IV characteristics of the combined diode configuration. Was something like this. We said that in this region, when your voltage is less than, this is minus V gamma, this is plus V gamma, the voltage across the diode, I'll call it Vd, when the magnitude was less than V gamma, it would behave like an open circuit, right? So the voltage can be anything, but the current across that is zero. Current through that is zero. So when the voltage, when it's going to behave like an open circuit, there is no transfer of energy between the inductor and capacitor. So whatever the voltage the capacitor was storing at that point, it will remain the same. It will hold it forever. Okay, so this is what we discussed in the last class. Now we'll start discussing what happens when I start connecting the diode in parallel with it, in parallel with the both inductor and a capacitor. So I'll take the simplest case where I connect a diode in parallel with both L and C. So first we'll start with the case where V gamma is 0. So this, when you assume V gamma is 0, the diode even though it's carrying a finite current, the voltage across it is zero, so therefore it dissipates zero power. Okay, so this model of a diode is what we will refer to as lossless diode model, because it doesn't really capture any losses. Okay, so it will be a lossless diode model. So first we'll start with the value of a voltage, initial charge across the capacitor. Say it has stored an initial voltage of Vx across the capacitor, and let's say we have a switch here, and I'm suddenly going to close the switch. The instant I close the switch, assume Vx, for example, is greater than 0. The instant I close the switch, a diode the diode will suddenly offer zero resistance, and it will instantly dissipate all the power or the energy that is stored across the capacitor. So I'm using the word dissipate here because even though the voltage across the diode is zero, there will be an impulse of current that will take the voltage across the capacitor from Vx to 0. Okay, so there will be an impulse of current in the diode. So therefore, you can say that it will have a finite energy dissipation across it, or power dissipation across it, energy dissipated across it. Okay, so even though the voltage is 0 across the diode, the current will actually be an impulse. So because of that, when you take the product and integrate it, you will actually get a finite energy dissipated across the diode. Okay, so the energy is instantly dissipated by the diode. Now what happens when I have a negative voltage across the capacitor? So in an inductor, now we are actually going to have a negative voltage across the capacitor, say minus Vx. So when you apply a negative voltage of value minus Vx across the capacitor, the diode will behave like an open circuit. Now because the diode is an open circuit, what would happen is that it will just behave like a regular LC circuit, a standard parallel LC tank. So there will be a flow of current in this direction. So this is positive, this is negative. So there will be a direct flow of current in this direction. Okay, and the voltage across the capacitor will start reducing. It will try to become less and less negative. So the voltage across the capacitor will reduce, and eventually, at one point, it will reach 0. Okay, now I haven't shown the diode here. There is still a diode which is actually connected in this direction. Now, at this point, inductor is carrying all the current in this direction. The current in the inductor has reached a peak value. Okay, and after this point, what would happen is that this inductor will now try to charge the capacitor, because all that energy is now stored across the inductor, as current. This inductor will try to charge the capacitor to a voltage slightly greater than 0. The instant that happens, the diode will conduct, and it will take away all the current. Okay, so now you should understand the voltage across the diode is 0. Current is also finite, so there is no losses across the diode. Okay, so the circuit will then reduce to simply a circuit like this. So the inductor will now keep carrying this current indefinitely, and the voltage across the capacitor will come to 0. Okay, so the capacitor will no longer store any voltage. It had initially had a voltage of minus Vx, but now it had come to 0, and all that energy is now stored in the inductor as current. Okay, to find the value of the current, you just simply have to use half Li square should be equal to half C Vx square, and from there you can compute your I to be Vx upon root of L by C. It's a very simple result. Or you can also write it as Vx upon omega naught L. It's just root of L by C is nothing but the impedance of the parallel LC, of both either the inductor or the capacitor with the resonant frequency. So this is where omega naught is 1 by root LC. Okay, so that's the behavior of the circuit. So inductor current will remain constant, and inductor voltage will go to 0 forever. I will just show it. In inductor voltage, the capacitor voltage will stay at 0, and all the energy is now stored across the inductor. Okay, now we will try and analyze the same problem, but we will now assume the diode is actually a lossy diode, meaning it has a finite cut-in voltage. The same problem, we will analyze it, but assuming that the diode has a finite cut-in voltage. So first I'll assume a positive voltage across it, which is Vx, a positive voltage, but this positive voltage Vx is less than V gamma. Now in this condition, we know that the diode will behave like an open circuit, Okay, so the diode is not going to conduct, it needs V gamma of voltage to conduct. Now the capacitor is now going to store the charge the inductor. When I say charge the inductor current will build the inductor current. The inductor current will increase, and then the capacitor voltage will keep oscillating between plus Vx and minus Vx. So here it is actually less than V gamma is above Vx. So it will just behave like a standard LC oscillator, the normal LC oscillator. Okay, the diode really has no role there. But what happens if there was a finite voltage across the capacitor, Vx is greater than V gamma? If your Vx is greater than V gamma, what would happen is that, again, we'll assume that we are suddenly, we had a switch here and we are closing the switch at t equal to 0. Suddenly, the diode will start conducting and it will bring the voltage across the capacitor to V gamma, suddenly, instantly, because the diode will actually have an impulse of current flowing through it. So it will dissipate some amount of energy. And the initial energy was initially, say, Vx square. The moment you connect it to a diode, the combination of a diode and inductor, so you should know that the current through the inductor cannot change instantaneously. Okay, so it's like connecting a very short impedance across the capacitor. So all the current will fully flow through the capacitor, through the diode. Okay, and that it will actually be an impulse of current because the voltage across the capacitor has to change suddenly. Because the diode model is a voltage source, it means the voltage across the capacitor is also changing suddenly. So instantly, the energy across the capacitor would come to half C V gamma square. So this energy, half C into Vx square minus V gamma square, this amount of energy is actually lost across the diode. Okay, you can very easily show that mathematically. You can assume that diode having a finite resistance and in the limit the diode resistance tending to 0, this result that you can actually very easily show the total energy lost is this. Okay, so once it comes to V gamma, once the capacitor voltage comes to V gamma, after that, or a voltage slightly less than V gamma, okay, so you are actually having a voltage of V gamma across the capacitor, a voltage say slightly less than V gamma. So there will be a inductor current flowing through the inductor because it has an inductor also has a finite voltage across it. So there will be a current flowing through it. So this is V gamma now. The voltage has come to V gamma. And this current, it will flow like this in the circuit. So what would happen is that, again, once your voltage comes to V gamma or voltage slightly less than V gamma, your diode is not going to conduct anymore. Okay. So from that point onwards, the voltage across the capacitor is going to, it's initially we started at Vx much greater than V gamma, and suddenly there was a jump of voltage here. Let me just show it at a different time. So I'm going to show t equal to 0 here. So the initial voltage across the capacitor was Vx. Suddenly there was a jump, a sudden change in the voltage. It goes to V gamma, and then from then onwards it will keep oscillating between plus minus V gamma. Okay, it's never really touching V gamma, but it's always slightly infinitesimally lower than V gamma. Okay, so that's what we would expect. Now we'll see what happens when I connect a negative voltage, when I charge the negative when I just charge the capacitor to a negative voltage instead of a positive voltage. So now I'm going to charge it to minus Vx and see what happens to this. If you remember in the previous problem, when you assumed a lossless diode model, all the energy was was transferred to the capacitor, the inductor in 1/2 cycle. So we said that it started from minus Vx and it went to 0 here in 1/4 of a cycle, and then it stayed at 0 forever. An inductor built a current, peak current, and it stayed at that peak value forever. So that's what we said happened in the previous problem when you assumed a lossless diode model. Now, if you assume a lossy diode model, first we'll start with minus Vx. The diode will behave like an open circuit. So the inductor capacitor voltage will start from minus Vx, and then it will slowly start to reduce in magnitude. It will go to 0. At that point, inductor current would have reached a peak value. Inductor current would have reached a peak value. Right now the direction of current doesn't matter. I'll just show that it has reached, the flow of current will be in this direction. It will be in this direction. Okay. So the inductor current would have reached a peak value. And after this point, the voltage across the capacitor, now the inductor will try to charge the capacitor in the opposite direction. When it reaches V gamma, at that point, the diode turns on and it will develop a voltage of V gamma across it. It will maintain a voltage of V gamma across it. Now, if you see, normally what would happen is that the current through the inductor will start reducing, okay, in a normal cycle, in a normal LC circuit. At this point, the voltage across the inductor is a constant. It's always constant and is equal to V gamma. Okay, so this value is actually V gamma here. It's constant and is equal to V gamma. So what would happen is that the inductor current, now inductor was initially having a current flowing in this direction. The instant the voltage across the capacitor reaches V gamma, the diode offers a very low frequency path, very low impedance path for the current. So the current will now start flowing through the diode. So you should look at it intuitively. If any amount of current flows through the capacitor, then the voltage across the capacitor will increase. It will go above V gamma. But the diode won't let that happen, right? So it has to draw in all the current, okay, to stop that from happening. So and that's what it will do. So the diode will now start taking current in this direction, okay. Now, if there is a finite amount of current flowing in the diode, then there is some amount of energy getting lost. So what will be now we'll look at the profile of the current across the inductor. The instant current reaches here, it was initially behaving like a sinusoidal function, right? It's like a standard LC circuit, so it was like a sinusoidal function. But at this point, the voltage across the inductor is constant. The inductor current was actually a sinusoidal current, but the instant the voltage across the the inductor is constant, what would happen is that there will be a linear decrease in the current. Now it will behave like a linear function. It will decrease linearly and reach a value 0. Right? See, we know that the current through the inductor is simply integral of the voltage across the inductor dt. So if the voltage across the inductor is constant, then it will be a linear function. The current will be a linear function. So at this point, the inductor current was flowing in this direction. Okay. And the value of the current had now become 0. But there is still a finite voltage across the inductor. Now the direction of the current has to reverse. The value of the current has to come to 0, but now the direction has to reverse. Okay. Now when the direction is reversing, so the voltage across this is now V gamma. So now the direction is reversing. It has to now flow from the capacitor into the diode. Okay, the circuit would be like this. So now we have come back to the old circuit wherein we assumed a voltage. If let's say the capacitor was charged to voltage slightly less than V gamma, then we said that it will just behave like a standard LC oscillator, like this, at this point. It will just behave like a standard LC oscillator. So at this point onwards, from this point onwards, when the current of the inductor becomes 0, the capacitor will now start charging the inductor and the circuit will do something like this. It will just go on like this. Okay, so from this point onwards, actually I have not shown the direction of current properly here. So if you look at it, when I'm drawing it in reality, that the current would be in this direction. So it would have reached a peak value at this point, and it would reduce here. From this point onwards, it will linearly reduce, and it will start rising again. So they both will continue forever like this. So this will be the voltage across the capacitor, and this will be the current flowing through the capacitor or the inductor. So this is the only difference, is that the slope, the way in which the current changes. I'm sorry. So this point here, the current will have a linear decrease in the value. Okay, there will be a linear decrease in the current value, and this sudden change, whenever you have such sudden transitions from sinusoidal behavior to linear behavior, it's happening because of a nonlinear element, which is the diode here. Okay, it's a highly nonlinear element. Okay, and that's why we are seeing such a linear increase. From a sinusoidal to a linear change suddenly. And even in a when you had an inductor and capacitor and series diodes, two back-to-back connector diodes in series with it, we were seeing some sudden jumps in the voltage across the inductor, and that happened because of presence of a diode. Okay, so that's it. And I mean, now that we have analyzed this problem, it's pretty trivial to analyze a problem like this. So let's say we have an inductor capacitor and we connect two back-to-back connected diodes in this fashion. So now what would happen is that these two back-to-back connected diodes are going to limit the amplitude of oscillation. If you look at this problem here, what did we see here? We initially started with a value of minus Vx. Even though it started at a huge negative value, it finally came down to just V gamma, the cut-in voltage of this diode. Okay, so this can be seen as a kind of an amplitude limiting circuit. It's going to limit the amplitude of oscillations across the parallel LC circuit. Okay, so even though I start with a huge positive value or a negative value, wherever we start, we are going to come back to finally, if let's say I start from plus Vx, it's suddenly going to come to V gamma and then oscillate like this. Or if I start at say minus Vx, again it's going to suddenly come to a value of minus V gamma and then keep oscillating indefinitely. The peak value will be between plus minus 2 V gamma. Plus minus V gamma. Okay, so that's the problem here. So in case if I want to have a higher limiting amplitudes, so you can just connect more diodes in series. Okay, I can just connect two or more diodes. So in this case, it will be the amplitude limiting amplitude of the LC circuit is going to be, it's going to oscillate if whatever voltage you store across the capacitor, it's going to ensure any voltage you store across the capacitor which is greater than 2 V gamma, it's going to ensure that the amplitude of oscillation is eventually going to be 2 V gamma. Okay, it's always going to bring it down to this. And here in the previous problem, we discussed how does the transition happen. I showed it in time domain. The transition will take place in a nonlinear fashion. The inductor current will be initially sinusoidal, and the instant the diode starts conducting, we saw that the inductor current was linearly reducing. It was reducing in a linear fashion. Probably I'll just redraw the inductor current. So inductor current was sinusoidal here. At this point, it then started to grow linearly like this. Okay. After this, from this point onwards, it's just going to behave like a standard LC circuit with an initial value of V gamma across it. Okay. So this is all about inductor circuits with diodes in it. I'll probably start second order systems in the upcoming lectures. Okay, I might also start a series of lectures on analog circuit design, which is MOS circuit design. Okay, so I'll probably upload it in the next video. I'll stop at this point.